So this problem says, find the magnetic force on the electron if the electron's velocity is 0, 100,000, 0. So a lot of times we're going to be given three-dimensional components for velocity. So it'll tell us the direction that the particle is moving in three-dimensional space. And here it gives us the magnetic field in three-dimensional components as well. It's saying 0, 0, 5. So we want to be able to draw a three-dimensional coordinate system and just kind of sketch what's going on. In this problem, there is a sketch already for us, but one of the conventions is to draw a sort of X when you create your coordinate system. Okay, and this could be representing the XY plane, see? Where the XY plane is laying down. So it's like a tabletop or something. And then you want to label your X and Y directions. So we want to use the right-hand rule for setting up a coordinate system to do that. So the X goes here, and then the positive Y goes here. It's basically like when you're looking from the top down, the Y has to be counterclockwise from the X. Okay, like immediately counterclockwise from the X. And then your Z would point just out of the page. The way you set it up though is using the right hand rule. So see the finger, like the pointer finger, is going to be the positive X direction. And then the middle becomes the positive Y direction. The thumb will be the positive Z direction. Okay, so this isn't really like finding a cross product or anything, but it's just another useful right-hand rule that we can use. All it's for is just setting up the three-dimensional coordinate system. You just have to memorize like which digit is which. Okay. So once you do that, you can make yourself a little sketch of the situation. And then you got to figure that your X component comes first. So that's going to be Vx here. And then this is going to be Vy. And this is Vz. All right, so the 100,000 is in the Y dimension, the positive Y dimension. So you just want to be able to show that your particle is moving this way. They also say that the magnetic field, though, is all in the Z direction, the positive Z direction. So this is Bx, By, and Bz. So that would be a magnetic field that's pointed upward. All right, now I'll label each of these. All right, there we go. Now we have to find the magnetic force on this particle. So the thing about particles is they can only feel a force if they have charge, velocity, and if the particle is moving the right way relative to the magnetic field. And there's a formula for it. It says that the magnetic force on any particle will be Q times V crossed with B. So, with that in mind, we can use the formula for cross product. Like we can rewrite the magnitude of it as Q times V times B times the sine of the angle between them. Now notice that I took the vector away because it's not a vector anymore right now. I'm talking about the magnitude or size of it. And then I can use a right-hand rule to determine what the actual direction of the force is. But this formula right here will always give you the magnitude of the magnetic force. So let's plug in, put an absolute value around it, and let's see, we would have negative 1.6 times 10 to the minus 19 times 100,000 times 5 Teslas sine of 90 degrees. All right, so that comes out to 8 times 10 to the minus 14 newtons. So this is just the magnitude. Now, one thing to keep in mind here is you want to think very carefully about the direction of the force as well, because that's all part of this. Like, we want to find the strength of it, certainly, but the direction is challenging to find. And we have a right-hand rule, but now what we're also going to have is a left-hand rule. So we would use a right-hand rule for positive charges and a left-hand rule for negative ones. The reason why is that positives and negatives, they react to magnetic fields in totally opposite ways. So if this was a positive charge, then I would use the right-hand rule on it. It would feel a force in a certain direction. But since it's an electron, the easiest thing to do would be to switch your hand to left-hand rule. All right, so let me show that here. I'm going to get rid of this. And since we're using an electron, let's use the left-hand rule to find the direction. The left-hand rule is going to look just like the right-hand rule. It's actually a picture of it above. In the right-hand rule, you see the first part of the cross product is your pointer. The second part is the middle finger. And then the result is the thumb, see? But notice that there's a Q out front of the formula. And that Q can be positive or negative, depending on the particle that's feeling the force. All right, so one way to just easily fix that problem of the Q for negative charges is to switch to left-hand rule because it points in the opposite direction as the right hand. So now with the left-hand rule, you point your pointer in the direction that the particle is moving, that's the velocity. The middle will be the magnetic field direction, and the left-hand thumb becomes the magnetic force on the negative particle. I'll draw the left hand. Okay. The middle has to point up. So this is the pointer here. This is the middle. There's going to be some other fingers here. And the thumb, in this case, points to the left. Let me draw the velocity. The middle finger shows the B field direction. And the result is going to be the magnetic force on that particle. All right, so now we can draw it in. And it seems kind of strange, it seems kind of just counterintuitive that there would be a force in that direction. But that's the way magnetism works on particles. So even as this particle moves in the positive y direction, it'll be pushed. Its path would be deflected to the left due to the magnetic force. All right, so when we give the direction, we can say that it's in the negative x direction. Or negative I hat, that's another way to say it. And then we can put the whole vector together into vector form. This could be a good final answer.